Welcome to this second organic chemistry tutorial. We are continuing from where we left off in our syllabus last time, and we'll be looking at Sn2 reactions. Sn2 reactions are also called as substitution nucleophilic bimolecular for reasons that we'll discuss later to do with its kinetics. Sn2 reactions are a single-step reaction with no intermediates, which is the key differentiating factor between Sn1 and Sn2 reactions. And the most important term associated with such kind of reactions in which there is simultaneous bond breaking and bond formation are called as concerted reactions. To go back in FIBSE, we learnt about reactions called as pericyclic reactions. And these pericyclic reactions also were concerted in their mechanism. So the term concerted only means that there is a simultaneous bond breaking and bond formation in a single step. The mechanism of the reaction is backed by a few experimental evidences, and the major experimental evidences are that which are derived from the kinetics, which happens to be the rate, and the second one is the stereochemical outcome of the reaction. So stereochemistry and rate, both of them indicate a particular mechanism that is being followed by such type of reactions, and which is what we'll be looking at just now. The reaction mechanism looks somewhat like this, wherein the nucleophile goes and attacks the carbon to which the leaving group X is attached to, and there is a 5-membered pentacoordinated transition state which is formed. This high energy transition state then breaks into the products, with the nucleophile attaching itself from the rear and the nucleofuge which leaves the system. An energy profile diagram thus is obtained, which reflects truly on the fact that there are no intermediates that are formed in this reaction. If you look at the reaction coordinate against the energy axis, you see that there is an alkyl halide, which is the starting material, which goes through to a high energy transition state, which was the pentacoordinated stage as we saw in the mechanism, and that rapidly breaks to the product. Here is a more specific example involving the hydrolysis of methyl chloride as a starting material in the presence of hydroxide nucleophile. It forms this pentacoordinated transition state, and that transition state is formed by acquiring an activation energy which is equal to a numerical value of 102.6 kilojoules per mole for this example. And this transition state then rapidly falls downhill through to give methanol and the chloride ions as product. The evidence of this mechanism come from the kinetic studies, which reflects that the rate of the reaction is directly proportional not only to the concentration of the alkyl halide, but also to that of the concentration of the nucleophile. And this correctly reflects in the fact that there is a single step mechanism proposed for Sn2 reactions, in which Rx and the nucleophile both are involved in the rate determining step, which is the only step of the reaction. The stereochemistry of the reaction also reflects on an Sn2 mechanism, wherein exclusively an inversion of configuration is seen at the carbon that is undergoing nucleophilic attack. Both these evidences reflect on a mechanism which is single step and in which the nucleophile attacks from the rear so as to lead to the formation of a product which has an inverted configuration. To account for the experimental observation of inversion of configuration, two distinct explanations were offered based on valence bond theory and the molecular orbital theory. The reason offered according to valence bond theory is that the carbon atom which is undergoing nucleophilic substitution changes in its hybridization from sp3 to sp2. This change in hybridization leads to an unhybridized p orbital that forms at the carbon atom undergoing nucleophilic substitution. The two lobes of the p orbital each overlap with the nucleofuge and the incoming nucleophile, which are diametrically positioned opposite to one another. This is the reason cited for inversion of configuration. Here is a ball and stick model of a molecule which is chiral, and a nucleophilic substitution happening at the chiral center, leading to an inversion of configuration. The It's also cited for why there should be inversion of configuration lies at the unhybridized p orbital stage. Now, if both the nucleophile as well as the nucleofuge overlap with the same orbital, the overlap efficiency will be low. And since the overlap is going to be low, there is going to be inefficient binding between the nucleophile and the carbon atom that needs to undergo nucleophilic substitution. And so as to maximize the overlap, which is what the valence bond theory is always based on, there is a thermodynamic possibility only of having the nucleophile and the nucleofuge being at diametrically opposite positions, so as to lead to an inversion of configuration as you go from the starting material to the product. The molecular orbital theory is a little more complex in explaining why the nucleophile should come from an opposite direction or an opposite side to that of the nucleofuge, leaving the carbon atom on which nucleophilic substitution takes place, and it is beyond the purview of the syllabus that you have at hand. However, the important thing to remember with respect to MOT is that the nucleophile comes and places its electrons to the carbon atom on which nucleophilic substitution is desired. And the placement of these electrons can happen either in the sigma molecular orbital or the sigma star molecular orbital. And both these orbitals result from the vacancy that is being created by breaking of the CX bond. To break this CX sigma bond, it is necessary that the nucleophile places its electrons into the sigma star molecular orbital of the CX bond, because an increase in the electron density in the antibonding molecular orbital results in weakening of the bond. And the sigma star molecular orbital of the carbon atom on which nucleophilic substitution happens is placed diametrically opposite to where the sigma density is maximum. And the sigma molecular orbital density is maximum between the carbon and the halogen, and therefore the sigma star density will be maximum diametrically opposite to it. And so as to weaken this CX bond, it is important for the nucleophile to come and attack from the opposite side. A second stereochemical evidence comes from substitution reaction on 2-octyl iodide, which happens to be chiral due to the presence of a chiral carbon atom. And if the substitution occurs in the presence of radioactively labeled iodine, in the sense that the radioactively labeled iodine happens to be the nucleophile that replaces the non-radioactive labeled iodine in the starting material, then there are experimental observations or experimental parameters that can be measured, like the rate of racemization and the rate of exchange. It was observed that the rate of exchange was nearly half that of rate of racemization, which proves that each exchange of I star with I led to an inversion of configuration, because racemization takes place when one molecule of R type comes together with one molecule of the S type so as to form a racemic modification. Let us spend some time in understanding why the rate of inversion is nearly half that of rate of racemization. When the first ion of I- goes and attacks an optically pure R configuration of 2-octyl iodide, it transforms the molecule of R octyl iodide into its S enantiomer. And when one molecule of S comes together with another molecule of R, two molecules come together and racemize. And because one inversion led to two molecules coming together to racemize, therefore rate of inversion is half that of rate of racemization. And it was seen that with an experimental error, the rate of inversion and the rate of exchange were nearly the same, indicating that each exchange led to an inversion of configuration, which is indicative of an Sn2 mechanism. This aspect of change of configuration was studied way earlier by a chemist known as Walden. And now we associate this change in configuration, or we know this change in configuration at the carbon atom undergoing Sn2 reactions also as Walden inversion. So Walden observed that when plus malic acid was treated with thionyl chloride, it gave chlorosuccinic acid of a particular optical activity. On the other hand, when the same molecule was treated with PCl5, it gave chlorosuccinic acid of the opposite optical activity. It indicates that either in step 1 or step 2 there must have been an inversion of configuration. By a series of reactions, he even changed the configuration of malic acid from one form to the other. He started with the plus form of malic acid, converted into plus chlorosuccinic acid by treating it with SOCl2, and then eventually on treating it with KOH, he got the minus form of malic acid. Even though he could not pinpoint accurately that which step led to an inversion of configuration, it was the first step towards designing a mechanism for this type of substitution reactions, because it conclusively told scientists, or gave evidence to the scientists, that nucleophilic substitution leads to an inversion of configuration. And that's how many years later Hughes and Ingold came up with the conclusive mechanism of Sn2 reactions, which stated that in a single step there is an attack of a nucleophile at the aliphatic carbon atom that needs to undergo substitution, forms a transition state which is pentacoordinate, and eventually leads to the formation of the product. To summarize what we've done so far, we looked at Sn2 reactions, looked at their mechanism, which involved a single step through a transition state which was pentacoordinate. The evidences for this mechanism coming from kinetic studies and from stereochemistry, and the account for inversion of configuration based on VB theory as well as molecular orbital theory, from which the valence bond theory is required from the syllabus point of view, which states that the carbon atom goes from sp3 to sp2 hybridized state as nucleophilic substitution is afforded at the carbon atom. And to end with, we looked at Walden inversion, which set it up for Ingold and Hughes to propose the mechanism of Sn2 reactions. Thank you.